let us continue with the finite element approach for the analysis of structural mechanics problems by this finite element approach. Already, previous class I told the 7 steps which are involved, which we have explained for the classical approach. Same approach we will adopt here also. Only the first 5 steps, they are a little bit different in the finite element approach. Whereas in the classical method, so it is slightly different. And last 2 approaches, that is post-processor unit, which will be done in the computers if you are using. The post-processor operation, they are same. That is the solution process as well as analysis of results, that is stresses and other things. The remaining things, so it is different here. Already I told the first step, that is discretization of the structure or body, so into various finite elements. So in this discretization, we are going to divide the structure into finite parts or finite elements which are being interconnected only at finite number of points, which we call it as nodes or joints. And all the unknowns in the problem are treated at the joints. How to select joints also I have already told in the previous class. Joints, preferably it has to be selected at points where load is there, concentrated load is there, where there is change of geometry. So we have to select a node, or where there is variation in the material property, we have to select a node. Or to improve the accuracy of the results, we have to go for higher order polynomial equations, so we need to have more number of nodes. Like that, already I have told. So only nodes has to be selected. How to select the nodes? How to number the nodes? That also I have told already previous way. There is certain methodology available, or you have to follow while numbering the nodes while discretization. So the number of the nodes should be such that while doing the analysis during the solution process, see the total space involved for storage of the data and computation, that it has to be minimized, and that the bandwidth has to be minimum. That also I told what is that minimum of bandwidth and what is the numbering of the nodes to be taken care. When numbering the node, you have to take care to minimize that bandwidth. And also the aspect ratio, the sizes of the elements, the ratio of larger size to smaller size, what should be the limit. All those things also previous class I have told. All those points has to be taken care while discretizing the structure. The next step is displacement model. So you have to select a suitable variable in the problem. Usually in our structural mechanics problem, the variable will be the displacement, either linear displacement or angular displacement. Of course, angular displacement is not the independent displacement, it's a function of linear displacement. It is after the first or second derivative of the linear displacement, that will be the angular displacement. Theta is nothing but dv by dx or dy by dx, where y or b is the translatory displacement. So independent variable only the displacement, and at all the nodal points we have to select a suitable equation for displacement. Take a suitable model or equation for the defining the displacement at the nodal points. So after knowing the displacement, the next step we can find the strain. And once you know the displacement, original geometry is known, so you can find the strain. Of course, strain is ratio of length, linear dimensions or area dimensions or volume dimensions, depending upon 1 to 3D problems. After all, it is just a ratio, non-dimensional So you can determine the strain. When one strain is determined, stress can be determined by multiplying the strain by appropriate modulus of elasticity. See, that's all. That's strain. Because we are working only with the elastic domain. It's an elastic analysis, not non-linear or plastic analysis. Within linear elasticity, after selecting the displacement model, we have to find the strain and stress. The third step is element property. This is the major thing, element property. In the element property, main property is determining the stiffness of the element, member or element stiffness. That is what we have to determine. This you can determine by using appropriate integral functions. Integral function is because when once you know the strain, stress, then you can use the simple equilibrium condition. That is total work done by the application of the force. That is known. So the total work done will be equal to the internal strain energy developed within the body as long as body or structure is in equilibrium. Total external force has to be equal to the internal stresses developed. That internal stresses developed we have to estimate. Of course, you have developed expressions for strain and stress. From that, they are nothing but internal stresses. So, which is opposing the external load. Using that internal stresses, on account of internal stresses, strain energy is going to be there in the body. That strain energy has to be minimum. We should not allow the structure to undergo strain. That should be stationary or in equilibrium. So you should not undergo any strain. That is why that energy has to be minimized. We apply minimization of that energy, strain, energy potential. So which is nothing but sum of that internal strain energy and external work done. That sum, if you take, one is opposite of the other. That difference, if you take, that difference is called energy potential. The difference, that's the potential energy of the structure, which will be extra within the structure, which will be the energy. That energy has to be minimized. Apply that minimum energy principle, you can develop an equation for the internal property, that is stiffness of the structure. The moment you determine this stiffness or internal property of the elements, all the elements which you have discretized, for all those elements you have to work out that internal property and then sum up to get the total structure stiffness matrix. Then fourth, assemble of total structure property. So that equilibrium equation for the entire structure, force is equal to internal, external force is equal to internal force. That is P is equal to K into D, where D is the unknown displacement. That is the unknown. K you have developed for the element and here for the entire property. Load P, external load applied, that is known. So D can be evaluated. That is fifth step, solution of equations or formation of equations, that solution of equations. So formation equation and sixth, solution of equations and last step, evaluation of unknowns. Evaluation of unknowns. That is displacement, internal stresses, either in the graphical form or pictorial form or in the form of numerals. You can evaluate. These are the 7 steps we are following, and these steps This is the post-processor. It's called post-processor. If you use the computer, this is called post-processing unit. This is process internal code in the computer. Whatever the work which is being done, calculations, that is the solution of the equations mainly, that will be done within the computer. And this major step is the data or preprocessor. Preprocessing unit, this is processing unit, this is post-processing unit. Three major processes which are going to be involved in the computer. And this preprocessor unit or the procedure you have to take care perfectly. Unless your preprocessing system, if you don't feed the data or formulate perfect data and feed it, your result will not be correct at all. So it all depends upon this data care. And of course, this is automatically it will be done, no problem at all. Nobody will be knowing it. It will be done within the computer. The solution processing document by whatever the method, either it may be your usual longhand solution of semantics equation or inversion or using material, whatever it is. Some process, standard programming, software programming is available. So using that, the solution will be carried out within the computer. Here, the code space and other things has to be saved. Otherwise, you don't get solution at all until come out. That is the reason why you have to prepare the data perfectly well to minimize this. The cost of everything, it will be involved mainly on this because this is the time processing. Here and all, it won't take much time. Preparing the data, you will prepare it immediately, within seconds it will take it. It will read, that's all. Then processing, that is a major computer time, CPU time, computer usage time. So their processing unit usage time, there you have to take care and reduce it so that the cost will be. And of course it is after all whatever it has carried out, that it will throw you out with the result in the whatever the fashion you like. So that is the steps which are involved in the finite element approach. Already this step I have already explained, except I have not told the various types of elements which we use for our analysis purpose. Because we are having here only one dimensional type of problem analysis, mainly in the structure process. So you have to, depending upon the type of problem, whether it is 1D problem or 2D problem or 3D problem, so you have to select different elements. A family of finite elements. So, type of problem. So, for one-dimensional problems, that is actually the problems which we have as per syllabus, only one-dimensional problems. Then you have two-dimensional problems, then we have 3D problems, three-dimensional. This already I have told in classical method of analysis. So 1D problems are those problems or structures wherein the structure is made up of only line elements. Here area elements. here solid elements. So that elements to be by which the entire structure is divided, I am going to sketch here, that's all. That's called family of finite elements. So usually, in the type of problem, we have first order problem, first order element, or it is called primary element, primary element. Next, you have higher order elements. To improve the accuracy, you are going to use more number of elements as well as more number of nodes, that already I have told, to improve your accuracy of the final results. To see that result is converged, you will go for higher order elements. Higher order elements by choosing more number of nodes. So then you have to take care of complex type of problem. You have isoparametric variety, that is called isoparametric elements. They are called isoparametric elements. So I will just explain what is the isoparametric element, what is higher order element, and what is primary basic element. So usually for one-dimensional problem, the basic element involved is a simple line. All your one-dimensional structures, they are made out of line elements I told. So line elements with nodes present at the ends. Unknowns will be only at the ends. So this is called the first primary element. So this is node 1, this is node 2, the basic element. In the higher order elements, so this 1, 2, node 1, node 2, left node, right node. So next, here in the higher order elements, you can choose one more node, internal node, or maybe one internal node, or you can choose more number of nodes. Maybe at 1/3 points, you can choose one node, two internal nodes, like that. These are all called higher nodes, because your displacement model will be different degree. So usually polynomial equation is used to represent the displacement model. So here it is only a linear polynomial. Here it will be higher order polynomials, second degree, third degree, nth degree, like that. So when you have higher order polynomials for defining the displacement model, it is called higher order elements. So in isoparametric type of elements, so to take care of your curved boundaries, so whatever the element you need, that is called isoparametric element. To define the geometry, whatever the parametric functions we are choosing here for displacement, same functions we choose for defining geometry also. That is called isoparametric element. Primary element is displacement model will be represented by certain equation, that the certain parameters, say called shape functions. The parameters are called shape function. The same shape functions which we use for displacement modeling, we use for geometry also. Altogether thing, we can remap the straight profile into a curved profile. That is called isoparametric type of element. So that they, or it may be 3 nodes or 4 nodes, whatever it is. This is isoparametric type of finite element we use. This is the major thing we have in your syllabus. Only the one-dimensional stress analysis, only the element property regarding the pertaining to this you have to take care. So in two-dimensional problems, since I am taking and defining the family of finite elements totally, so for other problems also I will sketch it. So the area element, simple area, this is mainly made out of by area elements. Here it is line elements, maybe straight or curved. Curved means it is isoparametric type. So straight having only nodes acting as first order or linear primary element. Others are all higher order elements, more number of internodes. Either it may be present or it need not be. You can remove that also during your solution process. The internodes to save your code storage and other things. Right? But to achieve the model, you may need nodes. Right? That is the only thing. Other than that, there is nothing much. So in two-dimensional problem, simple figure you can use is a triangle. Simple figure will be a triangle. Either a triangle having different sides, or it may be a triangle with one side with one angle 90 degrees. That is triangle. Or it may be a square, or it may be a rectangle. Perfect rectangle. Having nodes only at the corners, at the ends of the elements. The primary elements usually in this, not circle. Normal circle we don't use it. It's not circle to get the curved profile. We go for isoparametric negative. That's why yesterday when I explained the principle involved in finite element analysis through a circle, that circle we can divide by a two-dimensional similar figure, but triangle, simple triangle. I divided it and explained the process involved. That is the reason, nothing other than that. Right? The basic primary element is this two-dimensional element, triangle, or it may be rectangle with both sides. Then higher order elements, so you can have more number of nodes. So this is called linear strain triangle, realistic basic figure. Both linear strain triangle, not linear strain triangle, constant strain triangle, CST element, CST triangular element, constant strain triangle element. This is square element, this is rectangle element. Right? Next, higher order elements here are the same primary elements with more number of nodes. Like that. Internal nodes may be present at middle of the sides. This is called LST element, linear strain triangle element. 3-noded, this is 6-noded linear triangle element. So, or it may be like this also, it may be 6-noded. You can have 6-noded triangle, or here you can go for 8-noded square like this, 8-noded square or 8-noded rectangle, 8-noded rectangle or area element like that. Or it may be 9-noded also sometimes, especially to satisfy some conditions, we go for more number of nodes. Like that. This is one more node, internal node, middle, which is not connected at the boundary at all. This is called 9-noded rectangle element, 8-noded rectangle element, 8-noded square element, 8-noded triangular element. They are the higher order elements which we generally use in the finite element analysis for discretizing a two-dimensional figure. Then of course, isoparametricality, same parameter used for displacement used to define geometry, so it will take care of the curved boundaries. Like that, basic CST element or it may be basic LSP element, or it may be, instead of rectangle or square, we can have a quadrilateral, irregular shape, four-sided shape. We can have irregular boundaries. That's why I told you advantage of finite element analysis. You can take care of irregular boundaries, irregular shape, irregular geometry. So you can define the elements by quadrilateral. Quadrilateral is isoparametric variety of square. This is the primary element of this quadrilateral. You can distort this element into some figure, some fashion figure, by changing the equation for geometry also, defining geometry also. So, or it may be curved, like that. 8-noded quadrilateral element. It is no longer rectangle, it is quadrilateral. 8-noded quadrilateral curved one, or 9-noded quadrilateral. All these we call it as isoparametric variety of finite element. And of course, for three-dimensional problems, to idealize that entire structure, we can go for a simple figure, will be a tetrahedron. Simple figure will be a four-noded tetrahedron, four faces it will be having. So four-noded tetrahedron. Or it may be a parallelepiped or a brick type of element. Like that. It is called 8-noded brick or parallelepiped element. Simple primary figure for three-dimensional. Higher order, similarly, you will have more number of nodes. It may be a 20-noded brick element, like this. So 8 nodes at the regular corners, and then one in the middle of each member, like that. One in the middle of each member. So it is 20-noded brick or parallelepiped element. It is a higher order. And of course, isoparametric variety is curved one. Like that. Like that. Either it may be 8-noded or it may be 20-noded. So these are the types of finite elements which we use in practice, and for these elements we have to determine this element property. That is, we have to determine the stiffness matrix for all these elements. Stiffness matrix of line element, 1-noded, 2-noded, 3-noded, or isoparametric type. Isoparametric type is not a special one. It is only the subcategory of this linear one. Because same shape function we use for defining geometry also. That's all. Nothing other than that. Primary and this, they are similar. Here are these. So these two variety, of course, it is not there. Right now we don't have to bother much. Only I have introduced what are the different types of elements which we use or which we have in the computers, in the element library process. You have this. You can choose that element library to model your structure. When you feed the relevant data to the computer with respect to these elements and choose that particular from that element library. That is about the first step, description, all those details which already I told covered in the first class, as well as this, which are the family to be chosen. And here, of course, it is very simple for us. It's only 1D element, straight. This rarely you go for the, anyway, just we derive some element property with either. This is linear, this is quadratic, this is cubic element. Like cubic line element, quadratic line element, or linear line element, straight element. That is isoparametric variety. That's all the identification of each type of element which we use in finite element.